Alrighty, good morning, boys and girls, ladies and gentlemen. Welcome to another episode of Mr. Smith Talks About Calculus. Today we will be tackling section 3.6 out of Louis Leithold's seminal classic, The Calculus 7, so titled 3.6 Sketching Graphs of Functions and Their Derivatives. Which you will be pleased to know we've already sort of done in part. And in this section, we're just going to add a couple wrinkles based on our work with the second derivative. But we did see some of this at the conclusion of 3.4, looking at the first derivative test, that there was definitely some interplay that we could create between the graph of a derivative and its function and vice versa, kind of understanding what the derivative is telling us about certain characteristics of the function, and now what the second derivative is also telling us about certain characteristics of our function and its graph. So we're going to kind of bring that all together today and revisit some old territory, but also add in that new stuff with the second derivative. So let's just go ahead and get started. Share screen. There's my mouse. And there is the title to this lesson, which you may, of course, copy. Cool. So sketching graphs of functions and their derivatives, again, 3.6 in the Calculus 7. And the introduction is kind of uncharacteristically brief for Mr. Leithold. He just says, you learned in sections 3.4 and 3.5 how properties of graphs of functions can be determined from their derivatives. Okay. We now show how these properties can be determined from the graph of the derivative and then used to sketch the graph of the original function. All right, so that's what we're going to do, using the properties of our first and second derivative to sketch the graph of the original function. And so for example 1, it's actually a redo of example 4 from section 3.4, where we gave the graph of the derivative and asked you to come up with a sketch of the function. But now with this section, we're going to add in a couple pieces of information. First of all, we're going to get the zeros of the function, and we're also going to use our newfound knowledge of the second derivative to sort of feel out what the graph is going to look like. So kind of backtracking and seeing what that derivative looked like. So f prime of x, so do y equals f prime of x. It was kind of a cubic looking guy. So we had something like this. Then we had -1, -2, 1, 2, 3, 4, 5. The zeros of the derivative were at -2, 1, and 5, and it looked kind of like that. Okay. And in 3.4, this was all we had. Okay. And what we did was we figured out, okay, well, the zeros of our derivative are critical points and point to potential relative extrema on our function. And by looking and seeing, oh, okay, so when our derivative is below the x-axis, that means our tangent is a negative slope. So we are decreasing. And then at -2, it goes from decreasing to increasing. This must be a minimum on our function. And by that same logic, okay, now we're above the x-axis, we're increasing. we hit this spot at 1 and then we're decreasing, okay, 1 must be a maximum, and then the flip-flop at 5. Okay, and I know that was kind of quick, and we'll go through that same logic very deliberately when we lay out this problem in full, but that's what we did in 3.4. The additional piece of information we're getting here, or pieces, is that at 1, and I didn't draw this super great, but there is a horizontal tangent to our derivative at 1 and also at 3. There's another horizontal tangent. Okay, so what I've just drawn is the tangent, the derivative to our derivative, the second derivative. So at -1 and 3 is where we have second derivatives whose value is 0, which could be important. Okay, so sort of just aggregating all of the information that we have. And actually, let's be explicit about that, that this horizontal tangent to our first derivative means that f double prime of -1 is 0, horizontal tangent, slope of 0, and so too f double prime of 3 is equal to 0. So I think the way that I like to do these problems is just, as I said, aggregate all of the information that we have about f itself, about the derivative, about the second derivative, and then we'll kind of carefully go through and see what conclusions we can make about the behavior of f itself. So kind of off to the side, we can just jot this down. First, with the zeros, they're going to tell us almost always in a problem like this what the zeros of the function are, because based on the derivative, that's not information we're privy to. Okay? The derivatives graph tells us the zeros of the derivative and potential extremum of our function, but it speaks not at all to the zeros of our function. Okay, so that's information that needs to be explicitly given to us. And in this problem, we're told that the zeros of f, I never know if there's an e in here. No e. Zeros of f, we are told in the problem, are 3.5 and 6. Cool. So then we're going to say, do we want to jump that close? Yeah. We're going to say potential extremum well, the potential extremum are the zeros or non-existent derivatives, first derivatives. We can hopefully see that this curve appears to exist everywhere. So there's no critical points that are D and E, but the critical points based on this graph and the locations of our potential extremum then are at -2, 1, and 3. And then the other thing we care about is our potential points of inflection, which are going to be when the derivative to our derivative, our second derivative, is 0, which we identified as -1 and 3. -1 and 3. And I'm sort of laying out all of these points, aggregating all of this information, because this is going to be sort of the basis of the organization that we're going to do, that's going to allow us to sketch a relatively accurate graph of this function just based on this information. But these are kind of like the fence posts for that organization and for the sketching we're going to do. So what we're going to do is build a table. In the book, they do this vertically. I'm going to do it horizontally and maybe encourage you to do the same, because to me, laying out what we're about to do horizontally makes it maybe visually a little bit easier to see as you move left to right on the x-axis what is happening with this graph. Just my brain going from a vertical table to a horizontal graph, just this makes more sense to me. So what we're going to track in this table is f of x, f prime of x, and f double prime of x. Okay. And we're going to use these points here to kind of tell us which intervals we need to care about. So the smallest number we see is -2 as our potential extremum. And so we're going to first look at what happens from -infinity to -2 at all of these, for all of these functions. Then we're going to look at -2. What happens? We then go from -2 to 1. So -2 to -1. What happens in between there? At -1. From -1 to +1 is our next interval of note. And then at 1 is a location of interest. Then between 1 and 3 is our next interval, because 3 is our next interesting point. And then x equals 3. Then between 3 and 5, oh, we should do 3.5, huh? Yeah. So from 3 to 3.5, this is going to be tight, but we can make it work. X equals 3.5. That's one of our zeros of f. And then from 3.5 to 5, it's a little snugger, and then x equals 5. And I think we should be okay to not have 6 on the chart. We'll kind of just deal with that when we get there. This is, oh, but we do need on the right side. We'll figure that out when we get there. Okay, so for now, I guess I really screwed up by making this one so big. So now we're going to go through left to right, and using our graph of the derivative, make calls about, when possible, make calls about f, f prime, and f double prime. Okay. For f prime on this interval, we're really not privy to what's going on. We know that it's decreasing, but we don't know if the function values themselves are above or below the x-axis. So if you're unable to make a distinction or a call, just leave it blank. F prime, we know, is below the x-axis, so it's decreasing. Okay. F double prime, and this is where our surfboard might be helpful, the derivative of the derivative that looks pretty positive to me. Okay. So we are positive, which means we are decreasing. So f decreasing and concave up. Cool. Maybe we should make this 2. Okay, then we get to -2. At -2, we still don't know what f is because we don't have a rule for it, but we know for sure that the derivative is 0. And the second derivative is still positive. How do I know that? Throw your surfboard up. The tangent to our derivative has a positive slope. The tangent to the derivative is the second derivative, and so that's a positive. So here's like where we get some nice synthesis between 3.4 and 3.5. At this moment in time, we have a critical point on our derivative. We have a derivative that is 0, which points to the existence of a potential extremum. Now, 3.4 land says, we don't know what the second derivative is. We've never been really introduced to that. And so in order to make a call on this critical number, we would have to look to the right and see what happens to our derivative after this 0. Does it change signs from what it was doing? Does it go from a decreasing function to an increasing function? Or is it one of those weird fake out spots where it's still decreasing and it just kind of paused and kept decreasing and thus is not a relative extremum? And so to do that, we would say, okay, let's look at the interval between -2 and 1. And oh yeah, now we're above the x-axis. Now this first derivative is positive. There has been that change in sign. The first derivative tells us that this must be a minimum. We were decreasing, we zeroed out, and then we increased. 3.5 allows us to do that without looking to the right. We've got a 0 of our derivative. We check the concavity, which is distinguished by the positivity or negativity of our second derivative. Well, if our second derivative is positive, that means our graph is concave up at this horizontal tangent, which clearly also correlates to a relative minimum. So 2 ways to get to the same conclusion, that we have a relative minimum. Cool. On this interval, our second derivative, so from -2 to -1, is still positive. At x equals -1, our graph is still increasing. And I guess we could say this, that f is increasing, and we'll go concave up. Cool. Once we get to -1, derivative is still above the x-axis. We're still an increasing function, but now, no, we're fine. The second derivative, this is our 0 spot. This is our 0 spot. Okay. Before we can conclude that this is a point of inflection, though, we need to look to the right and see, does the sign of our second derivative change? So picturing this, we've been rotating clockwise, 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 concave up, concave up, concave up. We pause. And now yeah, and now that derivative has changed signs. Okay. And so the second derivative on the right side is now negative, and thus this is a point of inflection. On this interval, we're still increasing, so it's increasing, but it's just gone from concave up and then to concave down. We'll see what that looks like on the graph in just a sec. So f increasing, but now we are concave down. And this is also a sign, okay, we've gone from concave up to concave down. There must have been a point of inflection there. Okay, at 1, that's another 0 of our first derivative. Our second derivative is still negative there. And so using the second derivative test, we can conclude that this must be a maximum. Because if we are concave down at a horizontal tangent, that must be a relative max, which is then confirmed when we look between 1 and 3. This graph is below the x-axis, which means the first derivative is negative, and we see the first derivative test also confirms that we have a max at 1. Still negative here, so now f is decreasing and still concave down. At 3, our first derivative is still negative, but now our second derivative is 0, So we look to see, do we have a point of inflection there? Does it change? Does our second derivative change signs? Well, here it's negative, there it's 0, then it's positive. So yes, this is another POI. Still got a negative derivative, so we are still a decreasing function here, but now we've switched from being concave down to concave up. Okay. At 3.5, so in here somewhere, we still have a negative derivative. We still have a positive second derivative. So we're still decreasing and we're positive and concave up, but this is the existence of our 0 of our function. So that's gonna be helpful. Okay. And the fact that we're decreasing as we approach this means that, well, we'll come to this as we sketch it, but that means that we were above the x-axis to hit this 0. We're not coming from below, because in order to be decreasing and hit 0, you got to be coming from positive values. So then on the next interval, we are still a negative derivative, still a positive, so let's say 0 here, positive second derivative, and then at 5, there we hit a 0 of our derivative, potential extremum. The second derivative at 5 is still positive, which means that this must be a minimum. We are concave up. And then we can kind of be okay without seeing the rest of this. Well, when we get to it on the graph, we'll talk about the rest of this, but we've just, we physically don't have room. So now, here's the fun part. Now that we've gone through and kind of identified all of these places, we get to try to translate this into a curve. Now you might be thinking that doesn't sound like very much fun, Mr. Smith, but it kind of is. So let's find my straight edge. And let's, I don't know. What kind of axes do we want? Do it sort of near the middle of the page, I guess. Keep that in view, sure. Yeah. So what I'm going to try to do is kind of line up. It's going to be rough, but like this left to right movement with our x-axis. So like the vertical axis should be somewhere around here between -1 and 1. Yeah, that'll work out kind of in the middle of the page. And then your x-axis. Got it. We need to go from -2 to +5. Actually, +6. One, 2, 3, 4, 5, 6. -1, -2, -3. Got it. So this is going to be y equals f of x. This is where we're going to translate this into a curve for our function. You will notice that I have not labeled the y-axis because we truly don't know much at all about the y values of our function other than the zeros. Okay, so where exactly these turning points are, where these minimums and maximums are vertically, we don't know. Well, we know or should be able to figure out what half of our coordinates we're on, whether we're above or below the y-axis, but where they are specifically, no dice. So we're going to start by plotting the zeros of the function. So the zeros of the function, we're at 6 and 3.5. 6 and 3.5. Okay. Now, starting with 3.5, and I mentioned this as we were plotting it in our table. The question is, there's kind of several ways to think about this, because you're probably thinking, okay, this is a little bit troubling. Like, how do I know if this is going to go like approaching 3.5 from negative and then turn around and come back to 6? Or are we going to go from positive values and then sweep back up to 6? And the answer is there's a couple ways. Looking at our graph here, our table here, as we approach 3.5, the first derivative being negative all the way towards the 0 tells you that the function is decreasing. Now, maybe you can figure out a way, but I cannot visualize how we could be approaching this 0 from negative values and be decreasing. They are mutually exclusive. If we are approaching the 0 from negative values, the function's got to be increasing. So the only way to make that happen is to be approaching from positive values. That's one way. You could also then see, well, in between 3.5 and 6, there's a minimum. Again, maybe you can picture it, but I struggle to see, and there's only one minimum. There's no like weird stuff going on. How could we do a turnaround here and get a minimum? It makes sense if we've come from positive, go to the negative side, and then come back up to 6. Yeah, then there's a minimum there. So that's all evidence pointing to the fact that this curve is going to be kind of like that. Okay. So we also have a minimum. We have a minimum at 5. So at 5, I'm going to just kind of do a little horizontal tangent. Okay, horizontal tangent. Cool. Where are other? So yeah. So I guess backtrack real quick. So we've done the zeros of the function. We kind of have an idea of how the curve's going to behave around there. Okay. And I'm sorry, let's forget that I did this. I think it still makes sense to try to go left to right after we've done that. But I think establishing the zeros first of the function is helpful, because then as we go through and try to identify the maxes and the minimums, we have a better idea of what side of the x-axis they should be on. Okay, so starting with -2, we know that we have a minimum. We don't know what the minimum is, but we know that it's at -2. By doing this preliminary work and kind of saying like, okay, we're going to be approaching the 0 from positive values, that means that this minimum needs to be above the x-axis. Because if we tried to put it below the x-axis, it would need to cross the x-axis somewhere to come back down to this 0, which we already said these are the only two zeros. So at -2, we're going to have a minimum, and you can just draw it wherever you want, as long as it's above the x-axis. There's your horizontal tangent at -2. At -1, we're going to have a point of inflection, which for me, I like doing points of inflections, just kind of diagonal lines, and you can kind of just fake it. But let's say there's your point of inflection. At 1, we hit a maximum. Another horizontal tangent. At 3, we've got another poi. We hit that 0. Or concave up. Okay, that works. I already kind of cheated here, but at 5, we've got that minimum. And then at 6, we hit the other 0 and go on about our way. Okay, so now we're going to try to fit a curve to these constraints. So from negative infinity to negative 2, we know we're going to be decreasing and concave up until we hit this 0. So decreasing, concave up. We then hit the relative minimum. We're concave up until negative 1, which is our point of inflection. And then there's that kind of subtle change from concave up to concave down. We then hit that maximum at negative 1. Still concave down until 3, and then we get that subtle shift to concave up. The points of inflection are tough to fit sometimes, so just do the best you can and just make sure you're being clear, like, okay, here's the point of inflection. Don't make me guess. Then we're concave up, decreasing. Oh, this is not going to be that good. It's okay. That's why I really like pencil, but I understand we got to use pen sometimes. Come down. We're still, second derivative is still telling us concave up. And in fact, the rest of the way will be increasing and concave up. So kind of just fitting this curve to the constraints required by our first and second derivative, okay? And let's just kind of compare this to what we actually did in example 4 of 3.4, because it should look somewhat similar. The differences are going to be, I don't think we knew the zeros, and so we kind of fibbed on those, and we didn't have the specific points of inflection. So let's just see how this compares, flipping back in your notes a couple sections. So this was the corresponding example. And yeah, I mean, it actually turned out to be pretty similar. By chance, we just put this above the x-axis. We had that point of inflection at, or that maximum at 1. So in this one, we only had the extremum at negative 2, at 1, and 5. They didn't give us the zeros, but we actually landed pretty close to 3.5 there, and that would have actually been pretty close to 6. So you can see just based on the one derivative, you can get pretty close. And then what we did today just added some constraints that made it a little bit more precise. We knew exactly where the zeros of the function were, and we knew where these changes in our concavity, these points of inflection, were supposed to happen. Okay? And it's never going to be perfect. It's always going to look a little wonky, but as long as you are doing your best to reflect what should be happening, and when it's not visually the neatest, being maybe just pointing to this and saying, oh, okay, this is a point of inflection, if you have to, that's kind of all I can ask, okay? So that was example 1. I gotta run and do something right now, so I think I'm gonna just do a separate, pardon me, a separate recording. This is a pretty short section. There's only 3 examples. So for the second recording, we're gonna work an example also from 3.4 where our derivative has some D&E spots and seeing how we can make sense of that. Also in light of our second derivative. And then the third example is moving from a graph of f of the function to the graph of the derivative and I believe the second derivative. So those are the 2 examples that we will do in the second half of this lecture. But this is hopefully, you know, enough to get your feet wet if you just watch this and wanted to jump in and try, you know, numbers 1 through 6, I think, would all, actually like 1 through 18 are all moving from graphs of derivatives to graphs of functions. It's not until 19 that we jump from functions to derivatives. So just based on this, you can have a pretty good go at the assignment. But of course, the second half of this lecture will give you a couple more examples. All right, so that will be that. I'm gonna stop my share. I'm gonna stop my recording if I can figure out how to do that. Stop recording. See ya.